This video extends the content of the paper that introduces the flight stack for reproducible and customizable autonomy applications in research and industry. We first outline the key contributions of the paper and how it benefits the robotics community in terms of real-world applications, time efficiency, and reproducible results. After this, we will present the real-world experiments that have been described in the paper and show in-field video material of the indoor and outdoor scenarios, each with nominal flight conditions and system failures. Flight systems in research applications are becoming more complex over time, while at the same time posing the demand on versatility. A solution that arose due to this coherence are one-board embedded flight computer. Such systems are great for performing lower-level navigation tasks, but they do not allow easy modification of subcomponents that are of interest to various research questions in the field of control, state estimation, and navigation. The next common iteration within the robotics community was to switch to off-board solutions for easy integration and increased computational performance. The issue with this variation is the knowledge of the system setup over time, efficiency in development, and a missing ready-to-use autonomy setup. The system presented by this paper aims to provide a time-efficient and robust solution to these issues. The presented system can be used on a large variety of platforms per se, but we had to choose a variation for the real-world experiments. This image shows a block diagram of the flight platform hardware. The setup uses two Odroid XU4 to showcase the load balancing capabilities of the presented flight stack. We are now going to show experiments in nominal conditions and a subset of failure cases to show how the flight stack processes these scenarios. This scenario shows a nominal setup in a controlled indoor environment. The setup uses the laser ranger for too close to ground error and landing detection, as well as a camera for visual inertial odometry. In addition, ultra-wideband distance measurements are used for position triangulation. The user interface first asks for mission selection, determining different configurations, including the trajectory to be flown. The system now takes off, performs the mission, and lands. Dedicated output to the user shows the state of the system. Now, to the contrary, we had an accidentally loose ultra-wideband antenna. Ultra-wideband is not determined to be an essential system element, but the system is set up to hold the mission during a failure of this module and land if errors can't be resolved. Here we see how the antenna falls off mid-flight. The system now transitions to the hold state and waits for possible failure resolution. Since this mechanical issue cannot be solved, the system decides to land. The next videos show experiments in an outdoor location. The majority of the system is the same, but ultra-wideband modules are deactivated and a GNSS system with a low rate of 1 Hz is added. The same system is used in a scenario in which the camera fails mid-flight. The camera is seen as more accurate in position than the default GNSS for this scenario. Thus, after disabling the camera driver, the vehicle transitions to the hold state and waits for the recovery of the image stream. As soon as the image stream recovers, the vehicle continues the mission. To illustrate the benefit of this particular example, this flight shows how the vehicle behaves if the flight is continued after the image stream has stopped. The mission is started in the same way, but in this case, image failure is configured to not result in a hold state. This serves as an intentional example where persistent features that would be rediscovered in the scenery if the vehicle holds are not existent because the vehicle moved during the image loss. Thus, the vision information diverges from its previously accurate position, causes a positional step for controls, and requires a recovery time for the estimated pose of the system. This graph shows the difference between holding in place or continuing for the last two scenarios.